A single elevator rope, 16 millimeters of braided steel, can support 32,000 pounds. Every car hangs from 4 to 6 of them, each built to an 11-to-1 safety margin. So the real engineering question isn't whether these cables can hold 10,000 pounds. It's what happens in the fraction of a second after they don't, and why the answer begins with a system most riders never know exists. A modern elevator hoist rope is a marvel of over-engineering. Each 16-millimeter steel cable is certified to withstand at least 32,000 pounds of force before rupturing, a number set by rigorous standards like ASTM A123 and EN 12385. But in actual service, the cable is never asked to carry anything close to its breaking point. Elevator codes in the United States and Europe require a minimum safety factor of 5-to-1. That means the maximum allowable load for a single rope is about 6,400 pounds, even though laboratory tests prove it can hold 5 times more. This isn't just a nod to caution, it's a deliberate buffer against every variable an elevator might face. Sudden stops, uneven loading, minor impacts, and the slow accumulation of wear. Manufacturers publish these numbers in black and white. An 8x19 construction, the most common for passenger elevators, lists a minimum braking strength of 32,000 pounds for a 16-millimeter diameter. With 6 ropes supporting a typical car, the combined allowable load far exceeds the weight of the car and its full complement of passengers. The safety factor is calculated not just for static loads, but for the dynamic forces that arise when the car starts, stops, or encounters wind sway in a high-rise shaft. Even with all these allowances, the actual working load on each rope is usually less than half of the code limit. Some sources mention an 11-to-1 safety factor, but this figure comes from older British standards and is not used in current North American or European codes. If applied to a 32,000-pound rope, the allowable load would drop to just under 3,000 pounds, far below what modern practice requires. The 5-to-1 factor balances real-world engineering with practical engineering, ensuring that ropes are neither underutilized nor oversized. This safety margin is not a marketing flourish. It is enforced by regular inspection and strict retirement rules. If even a few wires inside a rope show signs of breakage, the entire set is replaced long before the cable's raw strength is ever tested in practice. The system is designed so that even if one rope were to fail, the remaining ropes have more than enough capacity to hold the car. In the rare event of a complete rope failure, other independent safety systems, mechanical brakes, speed governors, and pit buffers stand ready to prevent disaster. The raw tensile strength of the hoist rope is only the first layer in a deeply redundant safety philosophy. Elevator safety is not just a matter of using strong cables, it is a system built on redundancy and balance. Modern passenger elevators rely on 4 to 6 hoist ropes, each constructed in the classic 8x19 pattern, where 8 strands of 19 high-strength steel wires wrap around a central core. This configuration is not arbitrary. The combined capacity of these ropes means that even if one were to fail, the others can easily support the full weight of the car and its passengers. Codes require that the allowable load for each rope is far below its braking strength, so the loss of a single rope does not compromise the system. But the real surprise comes from the role of the counterweight. Instead of the motor hauling the entire mass of the elevator car, the counterweight, typically set at about 45% of the maximum rated load, balances much of the car's weight. This leaves the motor responsible only for the difference between the loaded car and the counterweight, dramatically reducing the force that needs to be transmitted through the ropes. For a fully loaded car, the motor may only lift a few hundred kilograms, not several tons. This design minimizes wear on the ropes and the drive system, and it is the reason elevator motors are often smaller than expected for the loads they move. The physics of movement depends on traction, not just tensile strength. The hoist ropes wrap around a grooved drive sheave, and the friction between rope and sheave, governed by a coefficient of friction around 0.30, translates the motor's torque into linear motion. If the friction is too low, the ropes would slip before reaching their breaking point. If it's too high, premature wear or damage could result. The system is engineered so that the ropes grip firmly under normal loads, with the tension distributed across all ropes and the counterweight keeping forces in balance. This means that the actual stress on each rope is a fraction of what the raw numbers might suggest. Redundancy, balanced counterweights, and controlled traction all work together to ensure that a single rope failure is not catastrophic. The motor does only a modest share of the lifting, and the system is designed so that the loss of one component does not lead to disaster. This layered approach is the foundation for the failsafe mechanisms that follow, making the image of a plummeting elevator more myth than reality. When an elevator car moves, an automatic system stands guard over every journey. At the heart of this system is the speed governor, a mechanical disc that spins in sync with the car's motion. If the elevator ever accelerates beyond its rated speed, centrifugal force throws the governor's weighted arms outward. This isn't just a sensor, it's a physical trigger. As the arms move, they trip a lever, which in turn releases the safety brake. The brake itself is a spring-loaded clamp ready to bite into the steel guide rails that line the shaft. This entire sequence unfolds without any need for electricity or computer input. The governor acts as a kind of mechanical brain, making a split-second decision based on pure physics. Modern elevator codes require a minimum of 5 independent safety layers, each designed to work even if the others fail. First, the safety brake, originally demonstrated by Elisha Otis in 1854, grabs the rails the instant the governor trips. Second, the governor itself operates on centrifugal force, not software, and is linked directly to the brake by a mechanical cable. Third, a buffer at the bottom of the shaft absorbs energy if the car descends too far, using hydraulic oil or heavy springs to limit the force passengers feel. Fourth, electromagnetic door locks prevent the car's doors from opening unless the elevator is safely stopped at a landing, defaulting to a locked state if power is lost. Fifth, a secondary brake on the motor shaft engages automatically if power is interrupted, holding the car in place regardless of rope status. Each of these safeguards is designed to function independently. If a cable snaps, the governor activates. If the brake somehow fails, the buffer stands ready. If power is lost, the motor brake and door locks engage by default. The system does not rely on a single line of defense. Instead, it layers mechanical, electrical, and passive protections, all governed by strict engineering codes. This methodical design means that even in the rarest of emergencies, the elevator's safety mechanisms act faster than any human could react, making uncontrolled free fall virtually impossible. Elevator reliability is not left to chance. Every hoist rope is subject to a strict maintenance regime that begins with the wires themselves. Modern ropes are coated with a polymer lubricant, a thin film that seeps between the steel strands. This lubricant is not just for smooth movement, it slows corrosion, reduces internal friction, and helps inspectors spot damage before it spreads. Over time, even the best ropes develop small cracks or broken wires, usually where the rope bends over the sheave. International codes such as EN 12385 and ASME A17.1 set a clear rule. If more than 5% of the wires in any rope lay length show breaks, the entire rope must be retired. This threshold is not a suggestion. It is a hard cutoff, enforced during annual inspections in cities like New York, where every elevator faces a certified check. Inspectors use magnetic flux leakage scanning to find hidden breaks inside the rope, and any deviation beyond the threshold leads to immediate replacement. But what if a total cable failure does occur? The ultimate test came on July 28, 1945, when a B-25 bomber struck the Empire State Building. Elevator operator Betty Lou Oliver was inside a car when the hoist cable snapped, sending her plunging 75 floors. As the car raced downward, the safety brake and pit buffer did their work. The buffer at the shaft's base, designed to absorb the car's kinetic energy, limited the deceleration to about 2.5 times gravity, a survivable force. Oliver was badly injured, but she survived the longest unbroken elevator fall on record. The incident proved that the mechanical brake and hydraulic buffer, working together, could turn a worst-case scenario into a story of survival. Recent incidents continue to validate these layers. In 2018, a Shanghai office tower experienced an elevator overspeed event. The car's sensors triggered a protocol that halted movement, locked the doors, and activated an emergency evacuation. No injuries were reported. The system functioned exactly as intended. These real-world cases, along with routine inspection data from New York City, where a 40% drop in elevator-related injuries has been recorded since annual inspections became mandatory, demonstrate that vigilance, preventive maintenance, and layered safeguards are more than theoretical. They are the reason elevator freefall disasters remain so rare. Elevator safety is not left to chance or a single cable. It's a product of physics, redundant engineering, and generations of rigorous inspection codes. Today, over 18 billion elevator journeys occur safely each year. In modern cities, trust in that system is not blind faith, but engineered certainty.